Hello everyone, I am Sagnik Jana. Today I am going to give a presentation about my review paper which is security in cloud computing using blockchain. So first I shall give an overview of cloud computing. Cloud computing is the provision of computing resources through the internet. Businesses have two options, either to buy service from a CSP or to maintain their own computing infrastructure. Using CSP is considered both cheaper and safer option as businesses do not need to maintain their own computing infrastructure and they do not need to worry about the maintenance. Despite numerous advantages in cloud computing, there are some security concerns that need to be addressed. In recent years, data breaches have become more prevalent, which compromises data privacy, confidentiality, data integrity, etc. It also affects users' trusts. Traditional security measures may not be sufficient to protect cloud systems. That's why we need innovative solutions like blockchain to address this issue. Now I shall give a brief introduction to blockchain technology. So blockchain is essentially a chain of blocks. Every block in the blockchain contains a cryptographic hash of the previous block. So if we change some data in a block, it changes the current block hash, which in turn changes hash of all subsequent blocks. Considering the fact that every node in the blockchain network maintains a copy of the blockchain, it is very difficult to carry out such large-scale tampering. That's why blockchain is immutable by design, and this immutability can be used to enhance the security in cloud computing. Now I shall discuss some existing works on use of blockchain to improve security in cloud computing environment. First is blockchain-based database to ensure data integrity in cloud computing environment. In this paper, the authors proposed a two-layer blockchain-based mechanism to protect data integrity in cloud federations. In cloud federations, multiple CSPs come together to provide integrated services. The first layer uses a permission-based blockchain to store evidence of all the operations on the cloud. This layer uses mining rotation consensus instead of proof of work for increased performance. Due to absence of proof of work, this layer provides weak data integrity guarantees. Periodically, the hash of current block on the first layer of blockchain is stored in the second layer. The second layer uses proof of work as a consensus mechanism instead of mining rotations. This is this is for strong data integrity guarantees. The integration between these two layers improves both performance and data integrity. The main limitation of this system is availability, since each transaction requires signature from all the cloud members, making the entire system vulnerable to single node failure. Next is an integrated architecture for maintaining security in cloud computing based on blockchain. Here, the authors proposed a model which uses multiple cloud service providers and blockchain-based evidence storage. The client hires multiple CSPs, and after a certain number of operations, every CSP generates master hash value for their database and stores it in the blockchain. The rate at which master hash value is produced and stored is determined by the rate of expansion of client's data and their capacity to cover blockchain transaction fees. The authors assumed that CSPs do not communicate with each other directly, so all the CSPs store their master hash value separately in the blockchain. Once the master hash value is stored in the blockchain, the client validates that all the CSPs stored the same value. By comparing the master hash value, the client can detect any CSPs with malicious intent as their values will be different. The limitations of this model are hiring multiple CSPs increases the cost substantially as client need to pay for each of the CSP services. The proposed method also doesn't offer any indication which specific data entries has been subject to modification. Next is a blockchain based log management system for cloud computing. This framework utilizes blockchain in fog computing to secure and manage logs. The system architecture consists of fog environment with multiple fog units, each containing multiple IoT or edge devices. Logs are useful information generated by IoT devices in the fog units. In order to collect and manage logs securely from smart devices, each fog unit is equipped with a storage server for logs, which is located in its gateway. To optimize the log data size, administrative and security logs are separated from other less critical logs, and only the administrative and security logs are published in the blockchain. A permission-based blockchain of logs is shared among all the fog units. Each fog node acts as a peer node in the blockchain. The use of blockchain provides immutability to the logs. The main limitation of the system is it is highly dependent on the fog nodes, which are subject to denial of service attacks. Next is data provenance in cloud, a blockchain-based approach. Data provenance is crucial aspect in cloud computing, which ensures the security and integrity of data by keeping track of all the changes made to it. However, existing systems lack transparency and security as the log information is kept at a private and centralized server. The authors presented a framework for establishing data provenance in cloud computing using blockchain technology. To ensure trust and immutability, the authors developed a distributed data provenance service with interested cloud users serving as nodes in the blockchain network. Any changes made in the cloud is recorded as a transaction and propagated to the blockchain network. In the proposed model, the author opted for proof of stake consensus mechanism instead of proof of work due to the time and performance limitation of proof of work. Uh, in the proposed model, a node stake is a function of utilized cloud resources, and the higher the stake a node has, the higher the probability that it will be selected as a leader in the next consensus process. Only the leader has the authority to add its block in the chain in a given consensus round. After the leader is selected, the leader broadcasts its block to other participant nodes in the network who can authenticate the block by validating each transaction within the block. The main limitation of the system is proof of stakes limitations such as long range attacks and nothing at stake attack. Potential side channel attacks by malicious users can disrupt communication, leading to security breaches. Next is blockchain-based data integrity verification in P2P cloud storage. The authors proposed a blockchain-based system for data integrity verification in P2P cloud storage. The system involves dividing data into strats, creating a hashed Merkle tree, storing the public part of the Merkle tree in the cloud and the private part locally. The root of the Merkle tree is stored in the blockchain for stronger data integrity. The verification stage involves the server calculating the hash digest for a chosen strat, sending it to the blockchain where a smart contract is running, which confirms the data integrity. The limitations of this model are client may not be aware of the data integrity issue until performing data validation. Malicious clients may tamper with the random number to deceive servers and extract money. Servers can potentially delete original data strat after it calculates the hash value for the first time, which could lead to false verification of data integrity. Now I shall compare different approaches which I have just discussed. Approach 1 and 2 both involve multiple CSPs for data storage. However, approach 1 has single point of failure because in approach 1 every CSP need to sign a transaction for the transaction to be valid. but approach 2 doesn't have single point of failure. Approach 1 purchases services from cloud federations, reducing CSP hiring cost compared to approach 2. Approach 2 stores master hash values, uh, while approach 1 and 3 stores complete evidence of all the operations for easier modification tracking. Approach 3 collects log at the gateway level to prevent tampering, while 1, 2, and 4 uh, involve CSP in log collection, which compromises log data integrity. Approaches 3 and 4 use Elasticsearch and a Provenance database respectively for robust log searching. 1 and 2 lack these features. Approach 5 uh, divides the data item into certs for confidentiality, but it lacks encryption. Now I shall discuss some future scopes. First is integration of different approaches. As different approaches have their strengths and weaknesses, it is possible to combine them to develop a more comprehensive and robust solution. Next is development of hybrid consensus mechanism. Different consensus mechanism has their strengths and weaknesses. A hybrid consensus mechanism can be developed by combining different already existing consensus mechanisms to best suit the cloud computing environment. Next is integration with machine learning techniques. So machine learning techniques can be integrated with already existing blockchain data integrity solutions for real-time threat detection and log analysis. So thank you everyone. That is the end of my presentation. Thank you.